Good morning, and welcome to this Conservation Applied Research and Development, or CARD webinar. Improve your commercial light levels and save on cost. Thanks so much for joining us today. We hope you and your families are continuing safe and healthy. Also, we want to thank you in advance for your patience with any technical difficulties you might have that are related to the fact that all of our presenters are connected remotely. I am Mary Sue Lobenstein, the R&D Program Administrator at the Minnesota Department of Commerce, Division of Energy Resources. With me today is Laura Silver, who is a Senior State Program Administrator at the Department of Commerce, where she reviews Utility Conservation Improvement Program triennial plans and annual status reports. Laura is the Project Manager on the research that is the subject of today's webinar,
Can you
and
all
she
hear
will
me
be
typing?
moderating the Q&A portion of our webinar. Our presenters today are Jennifer Lai and Ali Cardiel from Slipstream. Jennifer is a Senior Research Engineer at Slipstream and the project manager on this work. She has 15 years of electrical design experience. At Slipstream, she conducts electrical engineering and lighting design analysis for commercial and industrial new construction and renovation projects, with a concentration on energy efficiency and sustainability. Jennifer also supports field research with a focus on lighting and lighting controls, such as the one we are having today. Allie is a field researcher at Slipstream, she was the primary field researcher on this work. In that role, she installs, monitors, and troubleshoots field research equipment and maintains network communications. On this project, Allie also provided significant support for the data analysis and reporting of project results. We're very pleased to have both Jennifer and Allie here today for the webinar. Before we get started, I'd like to go over a few items for those viewing online so that you know how to participate in the webinar. Each of you should see a control panel somewhere on your screen. The location of the panel depends on if you are using your phone or your computer. If you're using your computer, you can expand and collapse the panel by clicking on the orange arrow. Please be sure to maximize your screen for the best viewing experience. By default, you have joined the webinar using your monitor's speaker system. If you would prefer to join over the telephone, just select phone call in the audio pane of your control panel and the dial-in information will be displayed. All attendees have joined the webinar with their audio muted. If you are having sound or audio issues, head up to the audio tab and click on sound check. That usually resolves any issues you're having, but if that doesn't work, try switching between phone or computer call-in. If you are still having problems, try closing out of GoToWebinar and opening it again. You can submit questions to our presenters at any time using the questions pane. Simply type your question and submit it. If there are questions we are unable to answer, we'll follow up with you after the webinar. This webinar is being recorded today, and the recording will be available at a later date on both the department's and Slipstream's websites. A copy of the slide deck for today's presentation is available as a handout in your GoToWebinar panel, and you can download it at any time. This webinar is one in an ongoing series designed to summarize results from research projects funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Energy Act of 2007. The purpose of the fund is to help Minnesota utilities achieve their energy savings goal. $2.6 million of this fund is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Results from CARD projects provide utilities with data to enhance energy efficiency program designs within their SIP portfolios. As you can see by this pie chart, CARD projects funded to date have been in all building sectors, as well as some that cross all or multiple sectors. The subject of today's webinar addresses the commercial sector and discusses results from the study, which characterizes light levels of LED-lit commercial spaces in Minnesota and quantified the energy savings from optimizing light levels in overlit spaces. Now I'll turn it over to Jennifer, who'll start us on today's presentation.
Thank you, Mary Sue. Hello, and welcome again to our presentation, Improve Your Commercial Light Levels and Save on Cost. To begin, we at Slipstream would like to thank our sponsor. This project was funded by the Conservation Applied Research and Development, or CARD program, under Minnesota Commerce Department's Division of Energy Resources the Minnesota statewide Energy Efficiency and Renewable Resource Program funded by Minnesota ratepayers. During today's presentation, we'll start with a brief background and objective, followed by the key methodology steps of the project. We'll then go into depth on the various results of the project and end with some conclusions and program recommendations. We'd like to kick things off by describing a bit about the background and the objective of this research project. Lighting in commercial buildings has been the target of energy efficiency programs for years, with the primary strategy being one-for-one fixture replacement. However, recent changes to federal standards for fluorescent lamps and more stringent codes have begun to erode these program savings. Market changes are forcing energy efficiency programs to look beyond efficacy-based per-product incentives. Research suggests that significant savings potential exists through task tuning of light levels and redesign of overlit spaces. However, the average light level in typical spaces in Minnesota, as well as associated lighting system characteristics, was not well understood. You may be wondering, what is task tuning? Well, simply stated, task tuning is the dimming of lights in commercial spaces so that the average light level is appropriate for the specific activities being performed. You don't need the same amount of light for someone reading fine print as someone working on a computer or someone watching a presentation. However, too often the amount of light in a space is higher than necessary, and this could be for a variety of reasons. In some instances, a lighting designer may not know what activity will be performed in a space. This could potentially be improved by a more integrated design strategy, or perhaps no formal lighting design occurred, particularly in the case of one-for-one LED retrofits. A contractor may simply install lighting based on rules of thumb or based on what they've done on previous projects. Or a lighting system may not have been commissioned, meaning the installation may not be consistent with the design intent. Tailoring the light level to match the specific need of a space is the next frontier of lighting energy savings, and it requires the ability to dim the lights. However, with more and more dimmable lighting, such as with LEDs and daylighting controls, this potential is only growing. So, how does task tuning save energy? Here, we see the light level provided by an ideal lighting system as a function of its power. As you can see, as the lighting power increases, so does the amount of light in the space. For this idealized, untuned lighting system, you would measure 50-foot candles of electric lighting, while this system used 500 watts of electricity. For this example, the recommended light level per the Illuminating Engineering Society, or IES, is 40 foot candles. Tuning adjusts the lights to these recommended levels, resulting in a power reduction of 100 watts. So that was instantaneous power savings. How does this play out in terms of energy savings? Here, we see a plot of our idealized example system's lighting power consumption over a typical day. Note that the system does not have daylighting controls, meaning that in the morning, the lights come on to their full power and remain there throughout the day before being shut off at night. After tuning, the lights still come on at the same time. However, they now come on to their tuned power instead of their full power. The difference in power savings summed over time is the energy savings. How might this lighting control strategy apply in Minnesota? How overlit or underlit are commercial building spaces? A characterization, including site visits to accurately measure light levels, fills this knowledge gap and will lead to increased energy savings. Slipstream designed and conducted a research study to provide Minnesota CARD with data that will inform customers on how to implement more comprehensive lighting upgrades that could include controls, lower wattage fixtures, and task tuning. We'll now briefly describe the steps we took in performing this research. The characterization study was comprised of both primary and secondary research. We reviewed studies related to this project, conducted a segmentation of Minnesota lighting based on U.S. Energy Information Administration data, interviewed Minnesota Energy Efficiency Program staff and a select group of stakeholders, and measured light levels in a representative sample of Minnesota businesses. We also explored several options for expedited assessments that could potentially allow for avoidance of in-person measurements or simpler protocols for measuring light levels. We used the results from the site visits and data gleaned from our literature review to quantify the potential for energy savings from optimizing light levels. We also distilled lessons learned to clarify effective approaches for conservation improvement programs, or SIPs, to reach this market segment. And now Allie is going to walk us through what we learned during the course of our secondary research.
Thank you, Jennifer. Our review of relevant research gave us a solid foundation to build on for the remainder of the project. To begin to understand the lighting landscape in Minnesota, we used the U.S. Energy Information Administration's Commercial Building Energy Consumption Survey, commonly referred to as CBECS. We used their microdata to quantify the magnitude of lighting energy, building types, space types, lighting types, and control types. Commercial and manufacturing buildings in Minnesota use approximately 5.3 billion kilowatt hours of lighting energy each year. 5 building types make up approximately 2/3 of the lighting energy. Manufacturing makes up 27% and education makes up 12%, making them the two largest market segments. Warehouse makes up 11%, office 10%, and outpatient healthcare makes up 6%, which are also significant portions. Therefore, we chose to concentrate on these segments for our site visits. However, IES light level recommendations are not based on building types. Instead, they're specific to space types and the activities occurring in those spaces. Within the major building types, the predominant and overlapping space types are open and private offices, conference rooms, warehouse areas, and corridors. We also included classrooms, since those were of interest to the Minnesota Department of Commerce program staff. We therefore focused on these space types for our site visits, and these space types make up the majority of the area in each of the major building types, which is what we're showing in the figure here. Open plan offices are ideal for adjusting light levels because the light levels and associated electrical power make up a larger portion of the total building lighting power and can be affected with just a single adjustment. This minimizes the time and cost of achieving savings. Other good candidates are space types with many similar spaces, such as private offices and classrooms, where the amount of light level adjustment can be determined in one space and then quickly applied to other similar spaces. Exam room spaces are not good candidates because they make up only a small portion of the total building area, and the tasks that occur in these spaces require higher light levels. Even where light levels exceed IES recommendations, feedback from medical staff has stressed the importance of having high light levels for diagnostic reasons. LEDs are inherently dimmable, meaning that their light output and corresponding lighting energy can easily be reduced in overlit spaces. LEDs are rapidly increasing their share of the new and replacement lighting market. They made up only 1% of the new sales market in 2012, according to DOE estimates, but this increased to 3% in 2014 and 12.6% in 2016. DOE projections estimated that by this year, 2020, LEDs will make up 48% of the lighting market. Using this information, we estimated the portion of commercial spaces with LEDs already installed in 2020. Across all the major building types, LEDs serve 11% of the total commercial building area. As the percentage of commercial spaces illuminated by LEDs continues to grow, so does the opportunity for task tuning as well as the implementation of other control strategies. Daylight harvesting is a lighting control strategy that automatically adjusts the electric light levels when sufficient natural light is detected. This is important since the photosensor set point can be easily reduced in overlit spaces, which would reduce the electric light levels during daylit periods. The highest penetration of daylight harvesting is in education. On average, 9% of the major building types have some amount of daylight harvesting. This proportion will continue to increase because of energy codes that require this type of control in spaces with natural light. Another form of lighting control is occupancy or vacancy sensing. Although these controls don't allow for simple adjustment of light levels, they will likely reduce savings that may be achieved by reducing light levels through task tuning. Therefore, it's important to understand their penetration across Minnesota commercial buildings. Of the lighting control types, occupancy sensing has the highest penetration, averaging 21.2% across the major building types. This control is most prevalent in education and least prevalent in warehouse and outpatient healthcare facilities. Now I'll turn it back over to Jennifer, who will share with you our key takeaways from the interviews we conducted.
Thank you, Allie. Slipstream completed 2 interviews with investor-owned utility staff, 3 interviews with energy efficiency program staff who work for municipal utilities and co-ops, and 1 interview with a program implementation contractor. We also interviewed 1 representative from the Northwest Energy Efficiency Alliance, a national leader in lighting market transformation. These interviews focused on collecting information on lighting-specific programs and projects to provide insight and identify barriers to implementing lighting efficiency measures. Key takeaways from interviews with Minnesota utility staff, energy efficiency program staff, and implementation program staff include that 60 to 90% of lighting program savings currently stem from 1-for-1 replacement of existing lighting with either integrated LED fixtures or tubular LED lamps. Lighting control prescriptive rebates have a much lower uptake, and overall, downstream incentive strategies are more widely used than midstream approaches. Challenges cited by commercial lighting program managers include concerns about future program impacts as savings decline over time because of more stringent codes and market saturation of LEDs. As a result, programs are looking to diversify sources of energy savings and are seeking new ways to promote deeper customer engagement. Another challenge cited is limited lighting design experts serving rural areas. Contractors serving these areas are typically looking for fast wins and may be less willing to take on projects with more complexity. Generally, program staff do not encounter significant barriers on LED retrofit projects. Paybacks are good. Capital barriers may cause project delays, but do not often prevent projects from moving ahead. However, lighting control projects are more complex, less cost-effective, and have seen lower adoption to date. Furthermore, measurement of light levels is not often done on lighting retrofit projects, and when it is done, it is most often to ensure that light levels are the same or higher than before the retrofit. Most program staff thought that light level optimization could be a viable future strategy if the economics are good for both customers and programs. They also viewed light level optimization as a potential opportunity for deeper customer engagement. However, program managers identified several challenges, including a more complex set of occupant preferences, particularly when people with different preferences share the same space. They also noted additional cost and time associated with programming advanced controls, particularly when considering and addressing occupant feedback. Also important would be careful marketing and messaging to customers to avoid the implication that the customer is getting less value from the original LED retrofit than expected. Working with lighting designers, electrical engineers, electrical contractors, and manufacturers is required to influence efficiency improvements in Minnesota lighting systems. We identified stakeholders working with lighting in Minnesota, and through in-depth interviews with these stakeholders, we identified how these program allies currently make decisions, to what extent they currently address light levels in their projects, and how a lighting optimization program offering would ideally be structured to achieve the greatest market impact. The results of these interviews helped us tailor the project scope and to identify impactful commercial lighting recommendations for future SIP initiatives. Our interviews with program stakeholders included manufacturers, energy efficiency consultants, electrical contractors, and lighting sales representatives. Key takeaways from these interviews include feedback that major lighting manufacturers have LED products capable of task tuning today, and that the incremental cost is small to none for dimming capable fixtures compared to code required controls. Generally, these stakeholders see overlighting as an issue, and the conversion to LED lighting creates spaces that could be task tuned to 75 to 80% of designed light levels. However, at the same time, they noted that individuals have different brightness preferences and that the perception of brightness is subjective. Additionally, the more volumetric nature of LED lighting in comparison to existing lighting plays a role in this perception of brightness. So, obtaining occupant feedback on light levels is more important than simply taking light meter measurements. Capital cost was certainly identified as a barrier to implementing systems capable of task tuning. Controls are often associated with increased complexity to install, commission, and operate. Beyond this, a lack of contractor and end user awareness of control benefits was also identified. It can take time to educate someone. However, once they understand the system, they often will begin implementing the system on their projects. This barrier is likely easiest to overcome with larger building or portfolio owners. And now Allie will step us through the results of the field study portion of this project.
Thank you, Jennifer. We spent the majority of the effort on this project visiting commercial buildings and measuring light levels. We visited a total of 36 buildings across Minnesota. The sites were mainly clustered around big cities like Minneapolis, St. Paul, Rochester, and Duluth, with several additional sites in smaller communities. Within the sites, we visited buildings from each of our target building types. We initially estimated that we needed to visit 45 buildings. However, it became clear as we analyzed the data that we would be able to meet a 95% confidence interval target with fewer site visits. We therefore lowered our target to 37 sites. We eliminated one education site because of its extremely low light levels and atypical lighting types for an education space, which left us with a total of 36 sites. Anecdotally, the manufacturing facility staff were just as interested in the light levels of their manufacturing areas as they were about the office spaces. While manufacturing areas were outside the scope of this project, this interest, combined with high lighting requirements of these spaces, suggest an opportunity for a program to support light level optimization in manufacturing production spaces. Within each of the major building types, We characterized the light levels in several of each space type. The characterization included the measurement of light levels in each space we visited. The reduction in overall building site visits translated also to a reduction in the number of spaces we visited. We did, however, still exceed our initial target of 44 private office spaces, since this space type is so prevalent across the major building types. And although we didn't meet our original target sample, we still did maintain target precision with respect to statistical significance. In retrospect, our assumptions in estimating the target sample size were conservative. More specifically, a higher mean illuminance led to reduced sample necessary to achieve our confidence interval target. Now I'll share with you some example photos of the types of spaces that we visited. These are photos showing examples of a typical private office on the left and a typical open office space on the right. And here we show an example of a typical conference room on the left and a corridor or hallway space on the right. And finally, these are typical photos of our last two space types, warehouse on the left and classroom, which is on the right. Within these buildings, we quantified the mean illuminance for our sample by space type. We then calculated the degree to which the mean illuminance differed from the IES recommendation for each space type and expressed that as the percent reduction needed to bring the mean into agreement with the recommendation. For all space types, the mean illuminance was higher than the IES recommendation. This means that energy savings could be captured by bringing the two into agreement. In open offices, private offices, and classrooms, the illuminance reduction potential is 40%, 37%, and 17% respectively. This reduction potential is significant considering the quantity of these space types in Minnesota. Conference rooms were also very overlit, needing a reduction of 34% to bring their mean illuminance into agreement with the IES recommendation. Corridor spaces were the most overlit, with a reduction potential of 86%. However, there is less opportunity for energy savings in corridors due to their smaller portion of overall building area. In addition, the IES recommendation of 5-foot candles for corridor spaces may be considered too aggressive a reduction by the facility staff and the building occupants, which would reduce energy savings potential. Warehouse was the only space type with a mean illuminance essentially on par with the IES recommendation, and it was overlit by 4%. This could be due to an increased design focus, since lighting energy costs in a warehouse are a significant operating expense because of fairly typical long hours of operation. When the mean illuminance and IES recommendations are presented visually, the difference between the two is very striking. We have included the 95% confidence interval on this plot to show that for each data point, we are confident that the recommendation falls outside the confidence interval range. The only exception is, again, for warehouse, meaning that we can't be confident whether warehouses are overlit or underlit. But it's fair to say that they are properly lit and have a low potential for energy savings statewide. The degree to which the LED mean illuminance differs from the IES recommendation is likely due to the nature of LED retrofit projects. These projects traditionally are one-for-one replacements of existing fluorescent lighting due to the prohibitive cost of modifying existing electrical infrastructure and drop ceilings. With little to no flexibility to adjust the fixture spacing, the LED light level is determined by the LED fixture's output. When multiple lumen packages exist for LED replacement fixtures, lighting professionals and contractors tend to default to higher lumen packages to minimize the chance of customer dissatisfaction from low light levels. This default position is made even more reasonable given that the replacement fixtures will still yield significant energy savings. This systematic overlighting of LED retrofit spaces represents a significant opportunity for programs to address. To wrap up our discussion of the field study, we are showing that when normalized to a per square foot basis, the technical potential for energy and peak demand savings may be estimated for a given project. The highest opportunities for savings occur in the office and education building types. As we have mentioned, we spent a lot of time performing in-person measurements of light levels of various spaces in buildings. Although the IES Lighting Handbook's procedure for calculating average illuminance is simpler than taking measurements on a 2-foot by 2-foot grid, it is still fairly time intensive and might not be practical for building managers, contractors, or program field staff to implement. We therefore investigated alternative approaches to estimating illuminance that would be quicker without unacceptably reducing accuracy. These expedited assessments included a reduced sampling approach, which involved measuring fewer points and using a more simplified calculation method than the procedure outlined by the IES Lighting Handbook, and photometric analysis, which involved estimating illuminance using computer models. The IES methodology for calculating illuminance in a space involves measuring many points and entering them into a relatively complicated equation. This can take a lot of time across multiple spaces. We envisioned a quicker method that either used fewer measurements, simplified equations, or a combination of the two. Using the data collected from this field study, we simulated 3 reduced sampling approaches, which I will briefly summarize. Method 1 involves taking an average of all the points and does not use the IES procedures formulas. For method 2, we calculated the average using fewer points, 1 of each type of point, and didn't use the IES procedures formulas. For method 3, we used the IES procedures custom formulas but measured fewer points. Method 1 appears to slightly overestimate illuminance for most space types. Method 2 appears to underestimate illuminance. And method 3 produces results that are closest to the actual measured. We therefore conclude that a building operator, contractor, or program implementer could save time by either measuring fewer points or using a simplified calculation without significantly sacrificing the overall accuracy of the calculated illuminance. Switching to the other approach we investigated, photometric analysis involves using computer modeling to estimate illuminance in spaces. This modeling is a common part of lighting design. It is quicker than field measurements since it doesn't involve lengthy site visits, and since it's already a part of many projects, service providers could rapidly deploy it for quick determination of light levels and corresponding task tuning set points. We wanted to understand the accuracy of photometric modeling in predicting light levels, so we developed photometric models and compared their illuminance predictions to our field measurements on a subset of 10 spaces. We used AGI32 software to complete photometric analysis for open office, private office, classroom, and warehouse space types. The analysis evaluated spaces both with and without partitions or racking, and space types with both integrated LED fixtures and LED tubular lamps. Overall, we found that photometric analysis does a good job of estimating light levels. Our models were on average within 4.4% of measured illuminance and had differences that ranged from 0.85% to 8.9%. We conclude that photometric analysis is a useful tool for evaluating illuminance values and identifying opportunities for task tuning and associated energy savings. Although models are less accurate than field measurements, the reduced time involved justifies the relatively small trade-off in accuracy. Task tuning is likely to be perceived as providing satisfactory light levels in spaces with high light level uniformity, like classrooms or private offices. This is particularly true if conservative assumptions are made while modeling. For example, assumptions of a light loss factor of 0.8 to 0.9 and reasonable reflectance values. In situations where model inputs are unknown, like partition heights or partition locations, the degree to which lights are task-tuned based on models should be reduced. For example, if the model predicts a space will be 20% overlit, the lights could be task-tuned by 10 to 15%. This may be relaxed in spaces with task lights, since occupants may supplement the ambient lighting to provide higher light levels only where necessary. And now I'll turn it back to Jennifer for some concluding thoughts.
Thanks, Allie. I'll start our discussion of conclusions and recommendations by sharing estimated achievable savings potential from light level adjustment incentive programs in Minnesota. These estimates are based on the LED percent reductions found in our study. It's important to note that these estimates are based on the current penetration of LEDs, meaning that as the percent of installed LEDs grows, so does the savings potential. In total, we estimate that adjusting light levels could potentially save Minnesota approximately 167,000 megawatt hours annually, with most of these savings coming from the office and education sector. This energy savings is equivalent to 15,500 typical Minnesota households' annual electric consumption, reducing greenhouse gas emissions by approximately 152,000 tons of carbon dioxide, or the equivalent of taking 32,000 passenger vehicles off the road for a year. It also equates to over $18 million in cost savings to Minnesota businesses. The savings potential estimate assumes 88% of Minnesota lighting across these facilities is first upgraded to LEDs by 2035, and that 58% of these lights are easily tunable. It also assumes a program achievability factor of 57.5%. We evaluated cost effectiveness under two scenarios: task tuning as part of a new building or major renovation project, and task tuning implemented in a retrofit scenario, assuming adjustments are made to an existing dimmable LED system. For both scenarios, we only considered the labor costs associated with adjusting the lighting systems, not the equipment costs of the lighting system itself. For each of these scenarios, we calculated simple paybacks as outlined in this table. With the exception of warehouse spaces, the cost savings and associated simple payback of task tuning LED systems are very good. Operating cost savings from reduced energy use are between just over 3.5 cents to almost 18 cents per square foot, resulting in a simple payback of between 0.3 and 1.6 years for new construction, and between 0.6 and 3.1 years for existing system retrofits. For warehouses, the lower savings potential from lower lighting power and task tuning lead to long, simple paybacks. Due to these short payback periods, we recommend that for the remainder of the space types that task tuning be implemented in new construction projects or major renovation projects in which a dimming system is already planned as part of the design. For the same reason, if a dimming capable system already exists in a facility, task tuning should be strongly considered to achieve cost-effective energy savings. So task tuning is essentially a trade-off between energy consumption of a lighting system and light levels in a space. When performing task tuning, it is important to balance energy savings with occupant visual comfort, as tuning that is too aggressive could result in high energy savings, but at the expense of occupant satisfaction. Complicating this balance is the fact that occupants perceive light levels differently, both among individuals and under varying situations. Because of this complication, we recommend that task tuning be conducted with occupant feedback in order to balance energy savings and occupant visual comfort. Although this could result in lower immediate energy savings, it would increase energy savings persistence, as facility managers would be less likely to override tuned controls based on occupant complaints. In summary, there is growing potential in Minnesota to capture energy savings from advanced lighting control strategies. LEDs are inherently dimmable and are gaining market share. Additionally, building codes will further drive the market toward dimmable lighting systems. Today, even when dimmable lighting systems are installed, tuning the system is not standard practice, and many spaces are overlit as a result. We suggest 3 approaches to take advantage of the savings potential from advanced lighting controls, ranging from a simpler, lower-cost prescriptive program to a more complex, higher-cost program, each with incentives based on a per unit, per square foot, or per kWh basis. Prescriptive lighting programs, the first strategy, are prevalent, and there's lots of opportunity for deploying strategies that promote optimization of light levels. In the Minnesota program interviews we conducted, tubular LEDs, which are generally not dimmable, represent a significant share of the rebate activity. It is already common practice to offer a higher incentive for dimmable LED fixtures as compared with LED tubular products. Incentives for reducing the number of installed light fixtures or tubes, a potential delamping strategy, is a way to reduce light levels with non-dimmable fixtures. Several Minnesota program interviewees did mention support for delamping through their existing commercial lighting programs. Prescriptive programs can also offer incentive bonuses for customers that install dimmable fixtures and demonstrate that task tuning has been completed. Although task tuning can be implemented separately from a lighting retrofit, it is more cost-effective to optimize light levels at the time of the lighting retrofit because it decreases the number of required site visits. Transitioning now to our second strategy. This study demonstrates that there is energy savings opportunity from implementing task tuning in facilities that already have installed dimmable LED lighting and the necessary controls. The savings potential can be captured by incorporating light level optimization into the scope of an existing program like retro-commissioning, which involves a comprehensive assessment of a customer's facility to identify and implement energy savings opportunities through optimization of lighting and HVAC controls. Utilities can also offer a standalone program that supports task tuning. Our site visits found that illuminance for spaces lit by whole fixture LEDs was lower than those lit by tubular LEDs. A program can provide guidance to help customers select the right lumen package. Best practice is to use photometric modeling to identify the right lumen package for a specific fixture selection and that provides the recommended illuminance for a given space. Additionally, several manufacturers provide controls hardware that can be layered onto existing dimmable LEDs to enable more advanced control strategies like task tuning, and these products can be incentivized. And now to address our third strategy. In the last 5 years, utilities across the country have begun deploying incentives for advanced lighting technologies like network lighting controls and luminaire level lighting controls. Network lighting controls refers to an intelligent network of luminaires and controls which are programmable through a software interface and have the capability to provide monitoring data on system performance. Luminaire level lighting controls is a subset of network lighting controls in which each luminaire contains a continuous dimming driver and integrated occupancy and daylight sensors, allowing for lighting control at a more granular level. In Minnesota, Xcel Energy offers incentives for network lighting control systems that are listed on the Design Lights Consortium Qualified Products list, is capable of high-end trim in addition to code-required daylight and occupancy controls, and has been properly commissioned. Many programs offer per kW or per kWh incentives based on custom calculations, although programs administered by Focus on Energy and AEP Ohio offer network lighting control incentives on a per square foot basis. And that concludes our presentation, and I'd like to ask Laura at this time to help with moderation of any questions from today's audience.
Great, thanks for that really great presentation. If you have not already done so, please type any additional questions into the Q&A panel and send them to us at this time. Laura, do you have any questions for Jennifer or Allie?
All right. Here's a question. How could a task tuning recommendation be delivered to a customer of a recent LED retrofit without implying their new LED lights are delivering less savings than expected?
Hi, thanks. That's a great question, a fair question. And I think the thing to keep in mind is that an LED retrofit likely has yielded a savings of 50% or potentially even greater in overall installed kilowatts. And that's, I mean, I think that most installations have met that expectation. However, customers are often focused on ways to get the most bang for their buck. And as a result, it's seldom that customers opt to pay a very small incremental cost to actually control their inherently dimmable LED fixtures that they're purchasing. The control savings are dismissed as insubstantial in contrast to the significant savings in making that transition from fluorescent to LED. But the savings from task tuning is definitely not negligible and certainly should be considered, especially at the time of an LED retrofit.
Thank you. All right. What is the best way to tune light levels during the day?
That's a great question too. So Slipstream, or Seventh Wave at the time, was involved in a previous project that wrapped up in 2015, where myself and another colleague actually went into various spaces and conducted a task tuning exercise. I believe one of the things that we can share with the group of attendees is a link to that previous study. There is a link to it on Slipstream's website. If you were to go to Slipstream's website, and I'm sure Minnesota Card's website as well, and you were to just do a quick search for task tuning, a link to that report for that previous study from August of 2005 would come up. And one of the things that we did include in that report specifically was a detailed strategy of how to conduct task tuning. But in a nutshell, what we did was obviously try to minimize the amount of natural light in the space by, say, closing blinds. We also then took light levels with the lights on and then immediately with the lights off. And so by taking the difference of those two light meter measurements, it helped us to isolate what amount of lighting in a space was being contributed by natural light and how much light was being contributed by the electric lights. And so by quickly taking our measurements in that space at each of those locations, both with lights on and lights off, allowed us to understand what that electric light contribution was and how light levels in that space overall could potentially be right size for the specific needs of that space.
Thank you.
Mm-hmm.
Another question. You talked about how important it is to get occupant feedback when doing the retrofits. How would you suggest going about getting occupant feedback?
Okay. So again, referencing back to that same 2015 study that was, again, funded by Minnesota Card, and where we did do light level adjustment, we made sure in that study to ask occupants of a space to complete a short survey, both before and after that light level adjustment. The survey asks not just about light level, but about visual comfort as well. So things that we want to keep in mind are, things like glare, reflections, contrast. Um, Anecdotally, occupants did share positive feedback following light level adjustments. And in a few instances, staff even requested further downward adjustments, dropping ambient average light levels below IS recommendations, likely because of available task lighting. Also anecdotally, I could share, we did encounter a few spaces, not all spaces are overlit, we did actually encounter a few spaces where light levels were slightly below IES thresholds. And when talking or obtaining feedback from occupants in those scenarios, some did ask for us to increase light levels, but others asked for us not to make an upward adjustment to increase light levels to bring them into agreement with IES recommendations. So again, obtaining that occupant feedback is really important, and I'm not recalling whether I've mentioned it, but in the appendices of that 2015 study, we do include an example of the occupant survey that we used for that project. So again, a great resource. I know that can be easily accessed from Slipstream's website. If you just did a quick search for task tuning, you would find a link to the final report. The name of that study was Adjusting Light Levels in Commercial Buildings, and again was published in August of 2015.
Great. And I just put the link to that in the chat also, that study, August 2015. So if people are interested, they can look there. And one more question. I imagine that classrooms and conference rooms in particular could vary a lot in size and activity or use. How would task tuning play a role in addressing this variability?
Okay, it does certainly help to understand for any space type the specific types of tasks that you're expecting to occur in those spaces. IES recommendations are based on the actual activity occurring in a space. So if we think about a classroom or a conference room, when we talk about appropriate light levels, a reasonable assumption, say for a classroom, might be that you're completing more paper-based tasks of like that involve reading and writing. So an appropriate assumption there might be 40-foot candles. Whereas in both conference rooms, both smaller conference rooms and larger conference rooms, I think a reasonable assumption might be that those spaces will primarily host face-to-face discussions or presentations, which would require a lower light level, perhaps something along the lines of 30-foot candles. Although it's not uncommon to say that a classroom space, while it might be used in a more traditional fashion, at some point in the time, the use type or the activity occurring might say transition to being used as a computer lab. And if controls were installed that allowed for a high-end trim adjustment, light levels could be tuned to meet new lower lighting requirements based on those computer-based activities versus those paper-based reading and writing tasks. Anecdotally, I could also share just a quick story that I was involved in the lighting design of a large conference room in a previous space that Slipstream occupied actually, that had a dividing wall splitting this larger conference room into two smaller meeting spaces. And it was those two smaller meeting spaces that were used more frequently day to day, but when we had larger group meetings, that dividing wall needed to open. And both those smaller spaces and that larger space needed to be sufficiently illuminated. So the ideal lighting design for that larger room placed a row of fixtures right in the center of the space, which of course conflicted with the dividing wall. Well, Slipstream being the type of organization it was, we of course incurred that small incremental cost to install controls that would allow for task tuning. And we used those task tuning controls to downward adjust the light levels because the solution to our design snafu was that we needed to install an additional row of fixtures, which forced the overall light level of the space to a light level that was brighter than one was needed. But by implementing, say, like a 25 to 30% reduction in the light level in the space using that high-end trim setting, we're able to right-size the light level and provide the ideal amount of illumination, both for the space as a large open space and when divided into two small spaces. So two great examples I think we shared today where that incremental cost can help when the needs of a space are either variable or perhaps change over the course of time. In addition to, I think what we've been talking about today is just energy savings overall.
Great, thank you. Looks like that's all the questions we have, so I'll turn it back over to Mary Sue.
Great. Thanks, Laura. And thanks for putting that link in the chat. If you have any follow-up questions about the card project, please feel free to contact Jennifer or Allie or Laura or myself. The recording of this webinar, as I said before, and the slide set will be available on the department's website in a few weeks. The final report in a couple of months, I believe. When available, you can link to either of these from the quick links on our Applied Research and Development webpage as indicated on this slide. This R&D webpage has additional resources and information related to the CARD program and to CARD research projects, which you'll want to check out. You can go to the rest at the bottom of this page and check it out. Thanks for participating today. We appreciate your interest in CARD projects. Before I leave, I wanted to take an opportunity to mention several upcoming CARD webinars. On the 20th of October, the Center for Energy and Environment will be discussing findings from their investigation of a dehumidification in Minnesota single-family homes. On November 10th, Slipstream will be back to talk about the energy costs, and emissions impacts of measures that both save electricity and shift the time that the load occurs. Finally, on the 19th of November, the Center for Energy will be back again to present results from their investigation of evolving residential cooling systems and loads in Minnesota. You can keep abreast of upcoming webinars and other news related to SIP by signing up for the SIP updates on our email list. You can use the link on this slide to do that. In the meantime, feel free to contact me if you have questions, feedback, or suggestions for the CARD program or CARD webinars. And one last final thing is that as a reminder, there'll be a survey to take at the end of this webinar. Please take the time to do that. That gives us important feedback. So have a great day and thanks again for participating in our webinar.
Yes, thank you.